Can you just tell us in plain language what quantum sensing is?
Yeah, so let's start with these qubits. So these qubits, they are really sensitive to perturbation from the environment. And if we can measure these perturbations, how they kind of impact the qubit precisely, then we can learn something about the environment. And so here, in this measurement process, we really rely on technology that was pioneered by our colleagues in atomic clock, in the engineering of atomic clock. Okay. Atomic clocks, your listeners may have heard, is this really amazing technology that can measure time with a precision that is really unmatched in nature. So they can tell us a precision of 1 in 10 to the minus 21. So that's about, if you switched on an atomic clock at the birth of the universe, it would be now off by less than 0.1 second. And so we can use these spectroscopic techniques, these quantum control techniques that people have developed for atomic clocks, and kind of translate those on measurements of our qubits, and now not to measure time, but to measure other perturbations like magnetic fields, like electric field, temperature, forces, pressure. And these are really things that are really difficult otherwise to extract in biological measurements, but they could really hold the key to understanding what happens in signaling pathways, what happens to post-translational modification of proteins.
Okay, so how is sensing, as you're talking about it, different from imaging or microscopy?
Yeah, so again, imaging or microscopy kind of tells you where individual biomolecules are, but it's not very good in telling you what happened to these biomolecules. And we often would like to know if biomolecule, for example a protein, has undergone a modification and became from something that is useful for a cell to something that is diseased and causes a problem to cellular function. But it's often really difficult to do that with existing fluorescent microscopy technology. Now, quantum sensors, they can measure magnetic fields. Once you can measure magnetic fields, you could look actually at very different type of signatures. But now with these quantum sensors, we can for the first time have NMR or MRI sensors that are the size of a molecule. And this is where I really get excited about quantum technology.
Exciting. And when we're talking about the work that you're doing, we're really talking about looking at cells and what's happening inside cells. And that's at the most tiny level. And one of the things I came across was that people may want to study an anthill, but the moment that you do something and you even put your finger into the anthill, you completely disrupt it, and it's nothing like what you were starting to study before. And in some ways, is that a decent analogy of what it's like trying to look at studying cells and why existing tools don't work that well?
Yeah, I think that's a very good analogy. So quantum, so generally you can build sensors that can be in principle really powerful but very sensitive, but they are bulky and they are difficult to kind of integrate into your target system. Now, we are not the first group by a long shot that is developing quantum sensors to study biological systems. In fact, kind of the technology that people have been using as qubits are based on small pieces of diamond called nanodiamonds.
Okay.
So these are diamond nanocrystals that are small enough that they can be uptaken by a cell. But the problem is, once you have these nanodiamonds in a cell, you quickly realize that they are not that useful for sensing or that they have severe limitation for sensing, because their size is 10 to 20 times bigger than your average biomolecule that you want to study.
Got it.
And furthermore, it's really difficult to bring this nanodiamond into the right location within a cell. Now, this is where really our work could potentially be a game changer, or one of the aspects where our work could be a game changer. So what we showed is that we can encode a qubit into a protein. So a protein is a particular type of biomolecule. Each of our cells has about 20,000 different type of proteins. And so these proteins are the size of a few nanometer in size, so about 10 times smaller than nanodiamond. But what's most important is that molecular biology has become really good in inserting the gene that encodes desired protein into living cells. And so what these cells do then is they express that protein that we use as a quantum sensor, and they not just express it, but they also make sure that these proteins are deterministically placed in the right location within a cell. And this is far from what a quantum diamond sensor ever could achieve, in my opinion. So we are 10 times smaller, allowing us to get much closer, and we have this ability for the first time to genetically encode our quantum sensors.